it'll turn out okay. My guest today is someone who's been on this channel many times before. We have yet to talk about his field specifically. Today, we are about to change that.
Wonderful. How's it going, Vandalia? How you doing?
I'm good. Other Vandalia.
Oh yeah, I actually hadn't noticed that before just now that we're both VAND. My my grandfather went by Van. I go by Vandy. He went by Van. I Have you ever gone by anything like that, or just Vandalia?
Uh, just Vandalia on here. I've gone by other names and my real life name, but never anything else. Oh, I used to be called a stealth photographer back in the day.
That sounds like it might have a creepy story behind it.
Uh, kind of, maybe not kind of creepy, but not. Back in the day when I still went to church, I was photographer. I was a youth director, assistant youth director stuff, and photographer, and I could get shots really good about people knowing it. Like people doing embarrassing things, like drinking a cola, eating something, and I could snap it really fast.
All right. I mean, yeah, that's certainly a skill. Yep. So, you wanted to yeah, I guess I don't actually talk about like my job and like what I do all that often. It comes up sometimes, but yeah, not like a tremendous amount. Um as you know though, I am an atomic physicist. Um and I'm an experimental atomic physicist, and I specifically work with ultra cold atoms. And so, yeah, I am not a nuclear physicist. The two are different. The nucleus is the thing in the center of the atom, right? With the protons and the neutrons.
You're the whole thing.
I'm the whole thing, which is really a story mostly about the electrons and mostly about the outer electrons. So the atom that I work with now the most often is strontium, and there are several isotopes of strontium. Strontium is I never think about how many protons they have. So I have to look this stuff up horribly embarrassingly, but I know that it has isotopes from 84 to 88 nucleons. And I think it's like 38. No, what is it? No, it can't be 38. No, yeah, it could. It's amazing the sort of thing. It is 38. Whoa, I pulled that right out of my butt. Okay. I could claim that I like knew that, but I totally didn't. Not even a little bit.
But so that's his atomic number, or
that's his atomic number. It is 38. It is 38 protons, and the species that I work with most often, it has 50 not electrons, that 50 neutrons. So it has a total nucleon count of 88. That is the most prevalent version of strontium that's out there. Can we like extend the thing that's flipping off the top of my head? Is that possible?
1 second.
So that it's all in one line?
There.
Well, or we could do that, yeah, too. But I haven't actually always worked with strontium. I've previously worked with rubidium and potassium. But the thing that's in common with them is that they all tend to be on the first or second column of the periodic table. And that's because a lot of what I do, the cool way of talking about what I do is that I shoot lasers at atoms, and I make them very, 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 very cold.
So are you the beginning of a James Bond villain in training?
Oh God, maybe. Actually, hold on. It just occurred to me that this might actually be a decent time to share a clip that.
Okay.
So my advisor was recently at the Boston Museum of Science, and share screen. And I guess they filmed this short that while he was there. So this is my advisor, Eric Cornell, not this guy, whose name is on the thing. This guy's name is Eric Cornell, and he was my advisor in graduate school, and he explains it like he has a lot more experience. So let him take the floor for a moment.
I won the Nobel Prize in 2001 for making the world's coldest stuff. And it had been predicted 70 years before, 75 years before, by Einstein and Bose, an Indian scientist, but had never been seen because to see it, you needed to have really low temperatures. And we couldn't make temperatures that low until 1995 when we could. We used lasers and magnets to cool down a gas so cold that the individual atoms inside the gas, instead of acting like particles, instead of acting like little pool balls bouncing off of the rails and falling into pockets, they started to act more and more like waves. Those waves overlapped one with another, and it formed this sort of ultra cold jelly, goopy cold stuff, which was called a Bose-Einstein condensate. When we finally had the version that got to the necessary low temperatures, and the condensate appeared, it was a miraculous sensation. It was really something. I won the
Yeah, so I can. So that's the sort of general way that of really getting to the core of the matter is we make stuff really, really cold with magnets and lasers, and then it stops behaving like normal particles, and it all kind of clumps together and behaves as a new type of state of matter called a Bose-Einstein condensate. I haven't actually made a Bose-Einstein condensate in a couple of years now, because right now we get the atoms really cold, but we don't actually need them to be all the way down in the ground state. That's what a Bose-Einstein condensate is. It's when all the atoms are so cold that all of the particles are in the same state, and it's the ground state. They can't get any colder.
Real fast for any kid that might be watching or little people, what is an atom? Basics.
An atom, yeah. So an atom, they're a bunch of little liars because they make up everything, right? And so atoms they're sort of the fundamental, they're the fundamental things in chemistry that you add atoms together to make molecules. So the atoms have a proton and maybe some neutrons at the center, and then they have a tiny little electron that has an opposite charge that's zooming all around it like crazy. And so the simplest atom is hydrogen. It just has one proton and one electron. But there are like 90 naturally occurring types atoms, and we sort them by how many protons that they have, which is normally how many electrons they have. But you can actually add extra electrons and rip them off too.
So what do you mean by naturally occurring?
So naturally occurring, some types of atoms have so many electrons and neutrons that they're not stable. They break into smaller bits, or they shoot off they sort of sputter out other things because they're too big to all sort of collectively stay together. The reason that happens is because in the nucleus, where all the protons and neutrons are, the neutrons, as their name might suggest, are neutral. So electrically neutral. They don't really feel the electric force much. But all those protons do, and like charges repel from each other, right? So in the nucleus, you have this other force that's called the strong force that sort of glues them all together. But eventually you get so many protons that they're just pushing themselves apart like too much. And so atoms that are larger than lead, lead is I believe lead is number 83 or 82. It used to be that bismuth is right above lead. And it used to be that I think bismuth was thought to be the highest stable element, where there was at least one isotope, one combination of protons and neutrons that would just, you could just leave it like alone in space and it would just chill forever. I think they found out that actually bismuth does decay, but it has like a half-life of like 1 trillion years or something. So you have to like look at a big amount of it for a long time to see any evidence of that. That's sort of the reason that we only have that only some elements are naturally occurring, because eventually they blow themselves apart. And you have to go all the way up to like neutron stars. Neutron stars can be thought of as atoms, but that's not the useful way of thinking about them.
So, if I remember my terminology right, the atomic number is the number of protons an atom has. The atomic weight is the number of protons plus neutrons.
Yeah, roughly, pretty much. So the atomic weight, I think more specifically, is it's like the weight of how much you would have if you had a 1 mole of it. And it's something that is determined kind of like by, because you can have different isotopes. You can have the example that I'm sure a lot of us are very familiar with is carbon. There's carbon 12. Most carbon out there has 12 protons and 12 neutrons, but not all carbon.
So wouldn't that be carbon 24 then?
Yes, that would be. Sorry, 6 and 6. My bad. Thank you. And I don't think about the nucleus that much. I normally don't even. I think about the atom as a thing that has different states, energy states, and I think about how you can move between those states by hitting it with photons. So I basically think about how you can make the electron on the outside of the atom, how you can make it go into different patterns that have, then the atom behaves differently. Sometimes the atom will be responsive to magnetic fields. Sometimes, but like the ground state of strontium-88 is not responsive to magnetic fields to first order. If you have a magnetic field, it's just like not going to really notice it much. But when you hit it with a photon that has exactly 600, that is exactly 609 nanometers wavelength, if you hit it with that color photon, which is red, we have a laser that is red that we shoot at the thing to make it do this, then the atom, the electron on the outside, or one of the electrons, will be excited, and it instead of orbiting like sort of closer to the nucleus, it starts orbiting farther out. And it turns out that when it's doing that thing, it's a little, it's a little chunk of electricity that's going in a loop. And what happens when we have something like that? A magnetic field. By the way, you guys, everybody in the chat, load up on this, because when I actually talk about my work, I can't actually like go down the magnetic fields or Satan route. Mostly, sometimes, like if the time reversal is some hot nonsense, but I do actually understand sort of how magnets work.
So, do the electrons have anything to do with forming molecules?
Yeah, they do. So the reason, for example, that oxygen is able to form 2 bonds with hydrogen and form H2O, which is water, the reason for that is that oxygen has a total of 8 electrons in its sort of normal everyday kind of life as out alone. Now, oxygen actually is very reactive because it really wants to sort of get 2 more electrons to fill its shells. This is a term that a concept that you probably learned in chemistry, because it's more directly related to chemistry, because when atoms start to bond together, you're getting into chemistry and stuff. But the crossover there is very I know it does, Regios. I know it ruins the joke, but yeah. But so oxygen wants to take on 2 more electrons, because when it takes on 2 more electrons, everything is it just kind of wants to. That's a very, very bad explanation. I haven't actually. There's a thing called electronegativity, which describes how strongly different atoms are prone to hold on to electrons that they can get from other atoms, for example, or that are just sort of free floating. Oxygen has a pretty high electronegativity. Fluorine, which is just one more above it, it has 9 electrons, and it needs one more to close that outer shell. It's got 2 electrons in the S shell that in the very near the nucleus, and then it has 2 more electrons in the S shell around that, and then the next shell are the p orbitals. Orbital is a better term than shell. And you can have a total of 6 electrons distributed throughout any given set of p orbitals, and then you hit 10. And the ability of an atom to sort of be chemically active is really very strongly dependent on how easily it can either sort of share an electron with somebody else, or it can be greedy. Hydrogen can share, oxygen is greedy. So oxygen grabs 2 hydrogens and it sort of hogs the electrons, and the hydrogens kind of have to chill out and be a bunch of beta cucks.
So does your atom of choice have any molecules it forms with other atoms?
I probably, I don't know what they are though.
Okay.
Because that's chemistry. Right? But when you, so like neon is right above fluorine. Fluorine is extremely reactive. Okay. There's actually, this is a great rabbit hole to like fall down if you're ever interested in it. There's this substance called FOOF, FOOF, which stands for 2 fluorines and 2 oxygens, and it probably has something to do with like its thing. This substance is so reactive that and like the way you form it is absurd. You have to put fluorine and oxygen together in an oven at like 700 degrees and then like cool it down, which just sounds like a recipe for disaster, because this stuff is so reactive that if you drop ice in it, the ice just catches on fire, which is pretty hardcore. And there's like this one research paper where this guy did like a lot of these different things with FOOF, not FOOF. And it, like reading through the paper, it's like, wow, this guy was just having the time of his life. He was like, it was an extremely violent reaction when we did this, and we had to be careful for doing the thing. And we observed a quite a flame when we dropped it in ice. I was just like, what are you doing? This sounds awesome. But yeah, it was so that's really like, but strontium is on the second column of the periodic table, so it would be more likely to give up an electron. The canonical example of sort of a bond when you have 2 atoms and one of them like basically totally takes it from the other atom is not actually water. That's a covalent bond. They really are sharing it a lot. Man, I hope nobody that like knows chemistry watches this and they're going to be like, oh, this guy has clearly never taken a chemistry course, which is true after my sophomore year in high school. Turns out not all physics departments in college require chemistry, which surprises a lot of people, but I did not have to take chemistry in college. But an ionic bond is when one of the atoms really basically takes the electron completely from the other one, and it tends to happen with atoms on the second to last row of the periodic table, like fluorine, and below it chlorine, and with atoms on the first row of the periodic table, like hydrogen, lithium, and sodium. So the most common example of an ionic bond is sodium and chlorine, sodium chloride, which is table salt.
Yeah, it's funny. I joked about it before. Like both water and salt. Like I joked about before. I think both of the elements that make up salt are poisonous, but salt is something you need to live.
Yeah. No. sodium, if you drop sodium in water, it will like spark and it might create a little flame. It's a sodium. The things on the outside, the things on the first row are extremely reactive. The things on the second to last row are extremely reactive. And as you go farther in from there, they become less and less reactive. However, the very last row, column of the periodic table are the noble gases. And those are totally unreactive. And that the reason they're unreactive is because they have all the electrons in exactly the pattern that they want. And like everything is in its spot and it doesn't need to do anything else and it's fine. It's just chilling.
Yeah. I like also people made a joke about how, I think people made the joke before about how hydrogen and oxygen are both flammable gases, but then water puts out.
Yeah, and it really is. It's one of the reasons that like if you read about people who are like, oh, you can just zap the oxygen and the hydrogen apart, like that's really energy intensive. But if you can do it, it's like the best fuel. Like liquid hydrogen and liquid oxygen, hydrolox, is like the best, most efficient rocket fuel in every way except for its like the actual amount of the size of your tank has to be large because hydrogen is not very dense. Even liquid hydrogen is not very dense. But per unit weight, it gives you the most thrust because all those when you have two oxygens, which is how it normally hangs out, like the oxygen we breathe is two oxygens together. That's molecular oxygen. If you hear people describe just molecular oxygen, they're talking about O2, even though technically O3, which is ozone, where you have I can't do a triangle of them. Yeah, like it's like that. Yeah, I guess that's a triangle, but like I always get distracted by the fact that there's two thumbs because I'm several weasels in a trench coat. Okay, I'm not very smart and I have a lot of weird hangups.
So O2 and O3, you're saying?
Yeah, O2 and O3 are both different forms of molecular oxygen, but when we talk about oxygen, molecular oxygen, like people mean O2. But I don't work with any of those. Those are all atoms that you've like heard of and stuff. I don't know how many people have heard of strontium.
One more before we go back to your thing. There is, I could be wrong, but there is no bronze molecule, right?
Correct. Molecule? This actually gets at a debate that I've some people don't think that bulk crystals, like most metals, like bronze, they don't consider those molecules.
That's what I was wondering.
And I have no problem considering them a molecule, but I get their point. They are not like it. There isn't a molecular formula.
It's not traditional.
There's the molecular formula for like a unit cell. And there's a strict ratio. Like probably bronze, it might have different like microscopic lattice structures and stuff, but probably there's a very quantitative, precise way of sorting the different types if there are different types.
Okay.
Because bronze means is a mixture of copper and tin.
Yes.
Right?
Yeah.
But you can mix it in different ratios. Like I think it's mostly copper, but like a little tin. But I honestly I don't know.
I was wondering because those are two elements mixed together, or like brass is like I think zinc and tin, or is it zinc and copper?
It's zinc and copper because both bronze and brass, both of them have the gold from the copper. Copper is an awesome element, but but bronze probably has, if you mix it in the right like specific ratio and like you cool it down at the right rate and everything. It probably has a very predictable structure of atoms. Like maybe there's 3 copper atoms, and then there's a tin one or something. But it's 3-dimensional, of course, and there's a whole thing. But from a physicist perspective, like, yeah, it's a bound state of more than one atom, which is like how a physicist would define a molecule. But it's not. It's not like a molecule with a molecular formula and like with a specific binding energy. Like there's a binding energy, by the way, it's the amount of energy sort of associated with either forming or breaking a bond. So when oxygen and hydrogen burns, the oxygen has to break apart, which requires some energy to like input to get it to start, and so does the hydrogen. But then when they form the water, they release a bunch of energy, which is, and it's good that it requires some energy to start, because if it didn't, everything would just catch on fire immediately. Or yeah, everything would just catch on fire immediately. I have data for this, for how fast they're moving, but it doesn't have to be molecules. They can be atoms. They don't have to be more than one.
So, real fast, since you work with mainly electrons and whole atoms, you probably don't work with quarks at all. Then, since you don't work with the inside the atom.
No, I don't even. I don't even work with protons and neutrons directly. I work with some of the effects from the nucleus, but in my world, the nucleus, it does 2 things that matter. Really, both of those are part of one thing that matters, and that's its angular momentum and its magnetic moment, which are very closely related. If the nucleus has a small magnetic moment, magnetic moment, by the way, refers to basically how strong of a magnet an individual like particle of it is. And it has a dipole. The word moment is a word that has, it may not be worth describing what it is. It just means that there is an orientation of like a magnet. It has like a direction, and if you put 2 of them together, they would like repel a little bit, and if you put 2 of them together like this, they would attract a little bit. Just like any normal magnet. You really can get quite far with just thinking about these things as tiny little bar magnets. It's simplistic, but frankly, if the simplistic model works, you should use it.
So, where do you find your atom of choice and out in the world?
I find my atom of choice out in the world from suppliers that sell us samples of it. That's all I got for you, man. Honestly, it's potassium is a lot more common than like rubidium and strontium, which I've used. The 3 types of atoms that I've worked with personally are rubidium, strontium, and potassium. Potassium you can get, the reason it's called potassium is because you can extract it from potash, which is a type of ash that you get when you burn certain stuff. Like lye is related to, I don't remember, dude.
Yeah, is that the thing that people tell you to eat bananas for?
Yeah. Potassium is in bananas, and it's the reason that bananas are slightly radioactive, because some of the potassium, some of them have 40 nucleons. Most potassium has 39 nucleons. So it has 20, I believe, or 19, I don't remember, protons, and then the rest are nucleons. And most of the time you have a total of 39. So potassium 39 is the most common form of potassium. But potassium 40 it's very rare. It's like 0.00001%, but that's still like enough to like. There's a lot. I mean, there's a lot of atoms in a banana. Most of them are potassium, but there's still a few billion potassium atoms, and you're going to get several, like a lot of those atoms. And potassium 40 is mildly radioactive. It's not a concern. You should not. The amount of bananas that you would have to eat for this to be a problem, you would die from you would die because you would have to like take a fire hose of banana slurry and just like launch it into your body, and then you would undergo a rapid unscheduled disassembly.
So that means it would be possible to have bananas as a nuclear power for the power of the world?
No, unfortunately not. But they are radioactive enough that like you can detect it. But it has a very long half-life. It's actually astrophysically relevant and geologically relevant, because like I was asked this question actually in my one of my comprehensive exams, which I was doing on the topic of planetary migration in gaseous protoplanetary disks, which for the record is not atomic physics remotely. That's the point of the comprehensive exam, of that comprehensive exam, is that they test you on things outside of your specific field, because if they're going to give somebody a PhD, they kind of want to make sure they're somewhat well-rounded. And it turns out that most of a big chunk of the energy that can occur inside the center of those disks, where no light gets in from the outside because it's opaque, is from decaying potassium 40 and from aluminum 26. And these are random facts that I remember.
So have you? So are you in? I think I asked this before, but are you? Is this a name on YouTube, or are you an actual PhD doctor in this thing?
I am an actual PhD doctor. This is my diploma.
Nice.
From the University of Colorado. I have a doc. Sometimes people are like, "What? You have a doctor in philosophy?" That's what PhD stands for. Below it says physics, Doctor of Philosophy in Physics, and I was officially awarded this. I wasn't there. I was out of the I didn't actually attend my graduation because it took me just a little over 8 years to get this piece of paper. I worked my ass off for a long time. When I was 11 years old, I was like, I want to earn this piece of paper. And I did. And it was pretty awesome.
So what was your two theses on then? Your master's and your doctorate thesis?
So I don't have a master's degree.
Okay, you skipped.
You don't actually need to in the United States in most programs. These are things that change. Regios, I'm not going to answer that question because I don't want to dox the other weasels. But what was I saying? Yeah, I didn't have to get a master's degree. I could have chosen to do a bunch of extra paperwork and gotten one, but I knew I was getting my PhD, and people if you get a PhD, also having the master's in that field is basically completely irrelevant unless somehow it was on a different topic.
Okay,
but then it's not about the topic really.
So it's not like a step-by-step thing. Yet you have to get the master's to get the PhD.
You don't have to. You don't have to. But if I had, you could leave the program. You have to do some extra paperwork, and you might have to write. I actually don't know, because basically, the thing I was describing, the comprehensive exam with the protoplanetary disk, that is the second comprehensive exam. The first one, by the way, isn't an exam. It's just completing 5 classes. It's not an exam. It's just completing the classes. So it's poorly named. But that's Comps 1. Comps 2, I had to study a topic outside of my area, atomic physics. And so I chose astrophysics, and I chose specifically when stars are forming. And I talked a little bit about this on Before Earth, which everybody should go and watch if you haven't seen it. Before Earth on this channel with yours truly and Vandalia, of course, and Landon Knoll. Nell? What was our other guest's name?
Ness.
Ness. Nell was could be worse. I got the first letters right. But yeah, so when star and planetary system formation, you get a big disk, and then like Jupiter can start here, and then it can sort of move out and in and stuff like that. And so I had to study that topic, and I had to write a 20-page paper, and I had to present a presentation on the paper, and then I had to defend myself when they asked me questions. This was not my thesis defense. That is a different time. I had to do two defenses, the Comps 2 defense and the thesis defense. And at my university, and this is, I think, becoming more and more common, it's actually that first one that is like the hard one that you are likely to fail and retake. Like a third of people at our university failed it and had to retake it. And most of those, probably I would say 90% of people eventually pass. But some people decide, physics isn't for them or something. I did pass on my first try. It was actually apparently kind of close. Apparently my paper was, thank you, was a little bit difficult to read. And I think that was because I had been staring and reading about this topic for like 2 months straight. And so I had kind of lost touch with how to communicate it. I do a lot better when somebody is there to sort of prompt me and ask me like kind of questions, because I genuinely have a difficult time noticing when I've lost the audience, I think. But frankly, I think I'm better at it than most people. I think most people are worse at it than me. Probably not most people on YouTube, because that's a self-selecting, thing, but most people in physics.
Yeah. So but your thesis is probably a better read or a worse read than a certain thesis.
I was cowardly and I didn't do it at the end, but I almost, and I could have done it, and my advisor would have been like, "This is like weird. Why are you saying this?" And I'd be like, "No, I want to start my thesis with the sentence, 'Hello, my name is Michael Vandegraff.'" I almost did it, and then I wimped out at the last second, and I didn't do it because I am a coward. But I wanted so badly to start my thesis with, "Hello, my name is Michael Vandegraff," and then continue it with, "in this book." Reggio's calling me out here.
So speaking of that, has any creationist or anything like that ever tried to debunk your work?
Oh, yeah. I mean, it depends on what you mean by my work. Most of them, if you mean like debunking quantum mechanics, yeah, it happens all the time. There's this guy, Mr. Slave, who's been puttering around in some of the discords that I frequent recently, who he thinks that he has developed a theory of everything that is entirely classical, which is just factually not true and also factually impossible. But he's not. I don't know if he's I don't think he's a creationist. He's not a flat earther. I know him mostly from flat Earth servers, but he's not a flat earther. Yeah, Al spoke to him on his so he apparently streams every like conversation he has. So if you ever see him on Discord, he's streaming. I have not watched that yet, Al, and I have not read his stuff, and I feel like I need to read his stuff before I have another talk with him. But
so do flat earthers try to are you like the enemy of flat earthers then, not creationists?
I actually argue more with flat earthers, yeah. The reason is that most of the arguments that come up are more directly physical, in terms of pertaining to physics, whereas in young earth creationism, with the exception of the heat problem, most of the conversations are biological or geological. And so I sort of focus on the thing that I can kind of do half asleep, right?
So the heat problem thing is your area then, or is that?
The heat problem is physics at a very, very, very broad level. The heat problem is conservation of energy, which is literally high school level physics. The specifics of all the different details, like lithification of limestone, that is a chemical process. But when you sort of zoom out and you're like, okay, the chemists say that it causes this much heat. Heat is a thing that physicists are very comfortable with. And we know how to do conservation of energy. Like, okay, if they're saying that all the ice came from a comet, we can be like, that's not how any of that works, because that comet had to fall and hit us, and its kinetic energy is way, way, way more important than the temperature of the ice, which is completely irrelevant in that calculation.
So let's go back to your thing. And so what do you do with your lasers?
So first I want to discuss a little bit why magnets are of the depth. Oh wait, no, that wasn't wrong topic. Sorry. So yeah, what we do with our lasers is we shine them on atoms, and the atoms become extremely cold. You may ask, like, but it's not like a solid chunk. Like, I don't have a chunk of strontium that I'm hitting with lasers. It's a vapor, a very, 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 very dilute vapor. We have a vacuum chamber, and then on one end of the vacuum chamber, we have a chunk of strontium. There is a chunk of strontium somewhere. And we heat that up with some heating element. We call it our oven. Very, very clever name. And strontium, like all molecules, will, when you heat it up, some of those atoms will fly off. They just will. It's called vapor and vapor pressure. It's how sweat cools you down. When you're sweaty, the evaporation, the fact that some of those water molecules leave, even though your skin is not 212 degrees Fahrenheit, which is the boiling temperature for water under standard conditions. But some of them still leave. Rubbing alcohol is the same way. So you heat up a chunk of strontium and you have a vacuum, so that basically then the only atoms that are bouncing around in your vacuum chamber are strontium, and also hydrogen, because there's always hydrogen, but ignore the hydrogen, it's fine. So we have strontium that's just in a vacuum. It's just bouncing around, and it's moving at roughly ballpark the speed of sound, but not all of them are. Some of them are moving more slowly. And then we hit them with lasers. And this is where people start to be like, what? I thought lasers heat things up. You're right, but not in this situation. Because what lasers do in this situation is, the reason we need to use a laser is because if you just use like a light bulb, basically none of the photons are going to have any effect on the strontium. They're just going to zip right past it. Isolated atoms in a vacuum are transparent to almost all colors of light, except for very specific ones. And those specific colors are the ones where that photon has exactly the right energy to knock the electron into a higher state. But the electron can only be in certain states. It can be like this, or it could be like this, but it can't be like this. It can't just be like in one shape, but like smaller. It has discrete positions and states that the atom and the electron mostly can be in. And so if you hit the atom with just the right color of light, then it will absorb that photon and that electron will go up into a higher thing. So we shine a photon at the atom and the atom absorbs that photon. Now, the other thing that you need to understand, basically like the one other super critical ingredient is the fact that although small, atoms totally obviously have momentum. Photons have momentum. They don't have mass, but they do have momentum. They have oomph. When they hit you, if you get pushed back a little bit.
Right. So what are photons?
Photons are the smallest particles or packets of light energy. A photon is the smallest amount of electromagnetic energy that you can have, like at a given frequency. You can have photons of any frequency, generally speaking. If you have like two mirrors, then you can only have them when you have like an integer number of wavelengths, and that is exactly analogous to only certain tones on a guitar string are allowed. But in just free space, like if you just have a rope, you can shake the rope and have it have any sort of wavelength you want. And photons are the same way, but for a given wavelength or frequency, those are two different words for the same type of thing. They're inverses of each other, but you can have a minimum amount of energy, and that energy is given precisely by Planck's constant h multiplied by the frequency. That was the thing. That was the beginning of quantum theory. Was when Planck, was it Maxwell Planck? I can't remember Planck's first name. I think it might have been Maxwell. But when Planck finally derived the black body radiation law, he used a mathematical trick where he said, okay, I'm going to say that the energy of light can only come in chunks, and there's a minimum chunk. And he was able to derive an equation that perfectly explained observations. And those observations are the color of things when you heat them up. A thing that people have seen for a long time. People wondered for a long time, why does an oven get red when it gets really hot? Why is it when it gets even hotter, it gets orange and then yellow and then white and then bluish eventually? And it's because the energy in an oscillating electromagnetic field comes in minimum chunks. And those chunks are photons. They are very commonly described as particles of light. I think that's a totally reasonable way of describing them, by the way. There's a whole wave-particle duality thing. One of the things about modern physics is that, like, don't be so fussy. Like, be fussy about the math, or be way less fussy about the words. Because the math is precise.
What?
So photons are the chunks of light, and they move at the speed of light because, it's light. And when a photon hits a thing, it has momentum. We also know what that momentum is. That momentum is Planck's constant divided by the wavelength. So it's a very like precise amount of momentum. And that means that if you have an atom just floating in space, imagine the atom is perfectly still and it gets hit by a photon and it absorbs the photon. It is going to start moving along that same direction that the photon hit it. So now you've changed the speed of your atom by hitting it with light. And where do you get the light? You get the light from the laser. So now we have a way of changing the speed of an atom by hitting it with a laser. But it will only absorb that photon if that photon is at just the right frequency. It needs to be just the right amount of energy because it's hitting an electron inside that strontium atom, and that electron needs exactly this much energy, 1.21 gigawatts, in order to go and be an electron hanging out in this state instead of just hanging out in this smaller state. There's not an in-between. It needs that amount of energy. So an atom will only absorb the energy from photons that to that atom are oscillating at just the right frequency. And if it does, then it will absorb that photon and it will be pushed backwards, just like if you were to catch a bowling ball in a wheelie chair like I have. However, there is one more piece in order to explain how laser cooling works. Because laser cooling is the trick of hitting atoms with only those photons from all directions so that any direction the atom is moving, it's going to get pushed back. And that last detail is the Doppler effect. Do you know what the Doppler effect is?
It's the
Just do an example. Make the sound.
I don't know how to sound, but it's like for like an ambulance, something is going closer to you. It sounds like one way, but coming further away, it was leaving you. It sounds like something else.
It's exactly. It's eon, eon. When it's coming towards you, it's high frequency. It sounds higher pitched. When it's moving away from you, it sounds lower frequency. Now, if the ambulance is stationary and you're on a train moving by it, same exact thing. It doesn't matter which one is moving. Motion is relative, hot tip. But so it matters the relative motion of the source of the sound and the receiver. And that's the Doppler effect. And the Doppler effect occurs not just with sound, but also with light. If you are speeding towards a light source very, 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 very rapidly, that light will become more and more blue compared to its original color. If maybe it started red and it becomes a little bit orange, maybe it starts ultraviolet and becomes an X-ray. Red and blue is higher frequency than red. So we say it blue shifts and when you're going towards the source of the light. And when you're going away from the source of the light, it's red shifted. So we have this atom, and our goal here is to use lasers to cool down the atom. And we've established that lasers are made out of photons, and photons have momentum. So when a photon hits an atom, most of the time it goes through it, but sometimes it's absorbed. And that means that the atom receives its momentum. And then, so now we have a way of changing the momentum of the atom. How do we cool things down? Cooling things down means, as somebody pointed out in the chat earlier, that you're taking the average kinetic energy of all of the atoms and you're lowering it. You're making the atoms go more slowly. That's what cold stuff is. Cold stuff is stuff where the vibrating atoms all the way down are moving a lot more slowly than the other stuff. That's what cold means. If the atoms are moving fast, it's hot. If the atoms are moving slowly, it's cold. It's about the kinetic energy. And so what we want to do then is we want to figure out a way, okay, how can we zap the atoms so that they all get cooled down? Because if we hit the atom, it absorbs it and it slows down a little bit, but maybe another atom hits it or something else, and so it starts going this other direction. And now we're shining a laser at it, but our laser has photons only of this frequency, and that atom is moving. And just like the person on a train going past an ambulance, as you go past the ambulance, or towards the ambulance, it sounds louder because you're approaching the source of the noise. And so atoms that are moving into the laser, if I shine a laser at you, the atoms that are moving towards the laser, they see the laser as a little bit more blue. And because they see the laser as a little bit more blue, that means that if you make your laser at just the right frequency, only atoms that are moving towards the laser will see the laser at the right frequency. Only atoms that are moving towards you will absorb your light. All of the other atoms, the atoms that are moving sideways, the atoms that are moving away from you, that photon just goes right by it because that electron sees that photon and is like, oh no, you don't have the right energy for me to like get up and do my dance. And so only the atoms that go right towards the laser will see it and be absorbed by it, which means that if you take a laser and you point a laser this way and you point a laser this way, atoms that are going this way are going to get slowed down by the laser pointing this way, and the atoms that are going this way are going to get slowed down by the laser pointing that way. So in this direction, atoms that are moving this way get slowed down. Atoms that are moving this way get slowed down. But atoms that are moving perpendicular, they're not really affected much by it. So you put a laser that way and you put a laser that way. But the atoms that are moving up and down, those aren't being affected by it. So you take a laser and you point a laser that way and you point a laser that way. And now atoms that are going in this direction or in this direction, or the combination, are going to get slowed down. But now the atoms that are going into and out of the screen, they're not affected. So what do?
2 more lasers?
2 more lasers. We take a laser and we point it into the screen, and we take a laser and we point it out of the screen. And then right there in the middle, where all of those lasers interact, you have this area where if the atom happens to wander in there, because it's bouncing around your vacuum chamber, it wanders into there, and any direction it goes in, it's going towards the laser, and it gets a Doppler effect, and it absorbs the photon, and it gets slowed down a little bit.
So we got 3 dimensions of the laser. What the 4th dimension laser?
Well, they're not. Man, that's a funny question. It's not really an applicable one, but it is a funny one. I mean, the atoms, they're all moving through time at the rate of 1 second per second locally. I mean, technically, proper time, special relativity. Don't make me explain special relativity. I'm not that smart. Really not hard. But so because of that, now we have a little spot where no matter what direction the atoms go, they're going against the laser. And so the atoms slow down. They slow way, way down.
So is this like
Very
a
fast.
is this like a Dragon Ball Z beam struggle thing?
Man, I haven't watched Dragon Ball Z in a hot decade or two. There's a lot less charging up. I remember watching Frieza and Goku when Frieza fought Goku, and he was charging up his spirit bomb for a week. I came home, or maybe I watched it before I went to school. I can't remember. And for a week straight, every episode was filler with him just charging his spirit ball. And I was just like, come on, what are we doing here? Is this Naruto? What's with all this filler? Never watched Naruto, by the way. Too much filler.
I already saw them all. You think Naruto has filler? You should watch its spin-off series.
Why would I do that? So that's sort of the main way that we slow down the atoms, is that we shine a bunch of lasers at one point in a vacuum chamber, and atoms that wander in there will absorb way more photons in the direction they're going, which push them back, than they will from the direction they're coming from. There is a balance, for the record. They're still absorbing. They are. This is the part where I'm starting to actually like be more precise and qualify. The big picture that I've given you is correct. It is correct. It's not the full story, but it is correct. That is how you slow atoms down. That regime right in the middle where all of the atoms are pointing towards each other, that is called an optical molasses. Optical molasses. Because molasses, like imagine you're in a pool of molasses, and that you have like scuba gear and stuff, so you're not just going to immediately die. Okay, you're still screwed, for the record. Sorry, but you're not going to immediately die. Molasses, the faster you move, the farther it pushes back at you. So you slow down very quickly, but it only pushes back at you when you're moving against it. It's viscosity. These lasers are imparting a viscous force. They're making a region of space feel like it's stuck in molasses, because every way they go, they're getting pushed backwards. When they get very slow, though, now it's just a little particle in a vacuum chamber that's moving very slowly. What happens to just like a random particle in a vacuum chamber? If you just like stop holding it, what happens?
It just stays there?
No. In a vacuum, imagine the particle is a tennis ball, and it's just in the middle of the vacuum chamber, and you're holding it, and then you let go.
That's it. Oh, God.
By the way, you're on Earth. This is in a laboratory on Earth. You're holding it, and you let it go. Imagine you're doing it with a feather and a bowling ball, and you're filming it for flat earthers to watch.
Oh, it hits the ground at the same time?
Yeah, it falls.
Okay.
I
was thinking, it's like, I would say, does it collapse, or does it expand, or?
We're talking about it's moving so slowly that it's basically still. And atoms, because these are still gases, they're ultra cold. They're way, way, way below their freezing point, but they're so dilute that they don't behave like substances behave at standard pressures. The pressure of our vacuum chamber is 1 times 10 to the negative 10 torr. Okay, I believe standard pressure is like 800 or 900 torr. So we're talking a factor of like on the order of a billion or a trillion times more dilute. If you open the door on the International Space Station, the pressure outside is on the high end for our experiments. The pressure outside the International Space Station is a little bit high to do our experiments. You can do them, but you would prefer to pump it down even more. So if you have one of those atoms, it's falling. And it turns out that when it's falling, like, you have to be moving kind of against the laser pretty fast for it to like really be pushing you up. So there's like a balance. And so the atoms fall. And as those atoms fall, they do have some temperature. So we have a bunch of atoms and they're trapped in this little area. By the way, that's where the magnets come in. The source of the magnets is to basically also, it's basically to like magnify the effect kind of the velocity. In essence, that's not fundamentally how it's working. But it basically means that now the one that's pointing this way is way stronger than the one that's pointing that way. If it's on this side. Now the magnets add a position dependent force. That's what they do, not just velocity dependent. The molasses is only velocity dependent. The magnets also give you position dependence, so that lets you trap them. But that's a lot more complicated to explain. And magnets are, of course, of the devil. They are satanic. So we're not going to talk about them too much. But if you take the atoms and you drop them, I just shared a screen.
Right.
No, not that one. Whoops. I thought I had stopped sharing that before. So these are images of our atoms. These are false color images. Okay, these are just monochromatic images, and then you put a color bar on them. So this is the cloud of atoms at the beginning. It's small and it's cold. This cloud of atoms is a fraction of a millimeter across, and we're taking a picture of it. And then we turn off all the lasers and we turn off all the magnets, and we let them go. And at first, it's not doing a whole lot, but it is expanding because all like those atoms. It's a cloud of atoms, and all the atoms are moving in different directions. And every time they get near the edge, they get pushed back in until you turn off the trap. You turn it off. And now all the atoms can just go in any direction they choose, subject to the only remaining force upon them, gravity. So they expand, but they also fall. You see how they're going lower and lower and lower?
And also bigger and bigger and bigger.
And also bigger and bigger and bigger. What this is doing, those atoms are falling under gravity, but they're also expanding away, because when you turned off the trap, they were all going in some direction, and now all of them are just moving ballistically. And so the ones that were going up went up, but they really quickly turned back around because they're all moving really, really slowly. And by how far it falls, you can calibrate your magnification. That's how we calibrate our magnification, is we're like, okay, we know what gravity is. So if they fall this far and we know how many pixels that is, that means that the magnification of our imaging system is that. And then you compare that to what you expect based on the lenses you chose, and those should be the same. And if they're not, then something else is going on.
So is this
these
for
atoms?
Sorry, is this for any atom or just particular atoms?
That's true for anything. I mean, this is true for molecules. This is true for anything, for any gas.
Okay.
If you get it cold and you release it in a big vacuum chamber, it's gonna fall down faster than it expands upward. At room temperature, you can't see this because it's just gonna it's zooming around at the speed of sound. That's why the speed of sound is the speed of sound, because that's how fast the molecules and atoms in the air are moving. But here in systems like this, the speed of sound is millimeters per second because it's so dilute and the temperature is so low. So the atoms fall. They fall and they expand. And they become this nice circular shape. And do I have a fit to this data? So if you look at the size of the atoms, here we're measuring the x-axis is time. Probably in nanoseconds. I don't actually. No, that can't be. What is this? Okay, this might be. They might have multiplied some stuff together, but you can fit this, and based on how big this is after you let it go, that tells you directly the temperature of that cloud. You are literally measuring how fast the atoms are moving. You're not measuring how much the mercury in your thermometer is expanding, which is a good proxy for temperature. Temperature is about how fast the atoms are moving. This is a direct measurement of atoms falling. It's probably, so this first one, they turn off the laser and immediately take a photo. This one, they turned off the laser, waited 2 milliseconds. I can tell because this is a 2 million here, because the unit of time that we use is nanoseconds. And the last image, those atoms had been falling for 30 milliseconds. These are all different experiments, by the way. Taking this data would take about 45 seconds to a minute and a half.
Okay, so none of these have been flying for a full second. None of these have been flying for a full second at all.
No, because how far does something fall in a second? If things fall in 1 second, they fall 4.5 meters. 1/2 AT squared is the equation, and A is equal to G, and G is equal to 9.8 meters per second. So 1/2 AT squared, when T equals to 1 and A equals to 9.8, is 9.8 divided by 2, which is 4.5. 4.5 meters is how far a thing falls without air resistance and without other forces in 1 second. Our vacuum chamber is not 4.5 meters long yet, because we're building one that is twice that, and then we're building a bigger one at Fermilab that is 10 times that. It's going to be 100 meters.
So you say we? Are you part of this building?
Well, I'm part of the experiment. I mean, like this here, I'm logged into our private wiki.
Ooh.
See, it says logged in as Vandy, and this is our wiki. This was the first cold atom cloud that they made in the lab. This is a better view of it here. You see that glowing ball?
Yeah.
That glowing ball, that is the location where lasers from 6 directions are intersecting. And right where those lasers all intersect is where they all stop and slow down. And because they keep on getting hit by light, and the light that we happen to use happens to be blue, it's 461 nanometers, because that is the transition from the ground state of strontium to the first excited state. It's more complicated than that, but yeah. So the temperature of that cloud of atoms is on the order of a millikelvin. It is 1,000th of a degree Kelvin above absolute zero. Okay. Room temperature is ballpark 300 Kelvin. So this right here is cooled down from room temperature, and it's actually coming from an atom that's like twice that temperature. But it's cooled down from room temperature by a factor of 300,000 just immediately.
So you said this is gas. Does it same work? Would it work the same with a liquid or a solid atom?
It would not. No, it would not, because those systems, the effect of all the other atoms that are pushing on it are much, much stronger. They don't behave like isolated individual atoms. The physics is much more complicated. This is where what the machine looked like several years ago when it was first being constructed. And we have 2 of them. We actually have 2 of them next to each other. And what this one is going to go like over here on the floor, and this one is going to go like 8 or 9 meters above it, up at the top of the lab. And there's going to be a long vacuum chamber that is going to be assembled in the coming months that connect those two. So we actually will be able to drop atoms and watch them fall for an entire second, which is pretty cool. I normally work not right here, but about like 6 or 8 feet to the left of this location. So it's all real stuff. And like this, these are other pictures of our atoms. Here on these ones, these are different stages of cooling that are, somewhat complicated. But here, guess which direction gravity is. These are atoms that are being cooled down, and they start to settle. And they settle at the bottom. And the reason it's circular is because of the magnetic fields. The magnetic fields mean that once they get to that position, that's where the laser is resonant. The laser that's pushing upward becomes resonant. So they fall down that far, but they don't fall down farther because the laser suddenly starts blasting them up. They don't fall up because things don't fall up. That's not how gravity works. And these atoms are very, very, very cold. These atoms are another 100 times colder. So at that point, we're starting to get into the tens of millions times colder. And the coldest that I've made atoms, the coldest that I've ever measured the atom temperature in one of my experiments was like reliably was 12 nanokelvin, which is over a billion times colder. It's like 100 billion something times colder than room temperature. So that's what I do. I also, this is actually data that I took. You can tell because it says Vandy. This was data that was taken by one of the graduate students, Rachel. She took that. I took this one. This is a different thing. All of these are actually the same. These are the same cloud of atoms, but imaged by different mirrors, all of which individually are shining on our on the camera. But that's interesting for other things about three-dimensional reconstruction of images, and less so for the direct atomic physics sort of angle. So yeah. Any questions?
I don't have any right now. Anybody in chat anything that they want to ask?
Al Trucker makes a good point. I actually almost brought this up when I was behind it. Propane is dense, but it's still a gas. Propane will fall if you fill a balloon with propane, and then you pop it without setting it on fire. Although if you do set it on fire, you can still sort of tell. It falls and spreads out on the floor. But you have been very, very delightful. And thanks. I have to say, the reason you've been, one of the reasons, you're delightful for all sorts of reasons. One of the reasons you've been delightful is you have not asked the question that I always hate it when people ask. Do you know what question that is?
And what's that question?
What is the practical application of this?
So, well, since you asked,
I'm a scientist. I don't like. Yeah, I brought it up, right? There are a lot of practical applications of this. Most of them are still kind of in development, but some of them are not. Ultra-cooled atoms are exceptionally good systems to build clocks out of. The best clock, the most precise clock in the world is operated not by, so I had I technically had 3, but one of them died in 2016. I had 2 advisors in graduate school. the one Eric Cornell, the Nobel Prize guy who was missing his left arm. I don't know if I mentioned. I don't think I mentioned that, but you may have noticed that like he had a big scar on his neck and his left arm is missing. Yeah, that's what flesh-eating bacteria will do to you. So if your arm is just hurting a lot for no reason, you should go to the hospital. Because if he had gone to the hospital like one day later, he probably wouldn't be around. They had to amputate a lot by the time they found out what was wrong. A great guy, by the way. Wonderful guy. So was my other advisor, Jun Yi. And Jun Yi, he operates an optical lattice atomic clock with strontium that is the most precise clock in the world. It's possible that that's not true technically right at this moment, but he has held that record for more than, I feel like more than 50% of the time over the last decade. So, because atoms, when you isolate them from all their other effects, they behave extremely predictably. And that means that you can shine a laser, and by seeing how they react to the laser, you know the frequency of your laser, and you can correct your laser and everything, and you can build a clock out of that. Where the second, instead of the second hand ticking, each tick is one oscillation of a photon. That occurs very fast, by the way. That occurs many, many, many trillions of times per second. Unlike the ticking hand of a clock, which occurs once per second, hopefully.
And this is the famous atomic clock people talk about?
Yes. This is the newest version of the atomic clock. The atomic clock came around in the 60s, but it's fundamentally the same idea, but more and more and more and more precise. Because the definition of the second is based on how long it takes for an atom of cesium to alternate between its two ground states. Probably in the next 10 years, they're going to change the definition of the second, and they might change it to being, there are a few candidates. There are some ion clocks with mercury and aluminum and stuff. But strontium optical lattice clocks, you have a whole bunch of these atoms that are all isolated individually in a lattice. That's caused by like a crystal of light. It would take a few minutes to explain, but each of those atoms is basically isolated completely from all the rest of them. The only thing that it's interacting with is the laser that's shining on it. And lasers, you can measure very, very, very precisely with atoms and also with ultra-stable cavities. Basically, you have two mirrors that are a fixed distance apart. And that means that only an integer number of wavelengths can exist between them. Just like with a guitar string, you can only have an integer number of wiggles because it's fixed at either end. And those clocks are so precise now. They're so precise that they can tell the gravitational redshift from the bottom of the sample to the top of the sample. And these samples are about the thickness of a human hair. And they can tell the gravitational redshift. That's a general relativity effect that used to require giant experiments with buildings and launching radioactive gamma rays from one side of it to the other, or looking at the planet Mercury in order to detect. Now we can measure the effects of general relativity on microscopic scales. Clocks are becoming so precise that the gravitational effects of people walking by them are going to start to matter. The gravitational effects of the water table underneath the building will matter. Clocks in Scandinavia cannot be synchronized long-term at the same rate because Scandinavia as a whole is rising at 2 centimeters per year. And that means that the clock in your lab is rising at 2 centimeters per year, which means it's getting farther from the center of the Earth. And we are in a hot season for clock technology. Regios, I think, might have seen a little bit of what this is about, because We are at the dawn of a new era, not of optical clocks. Well, yes, optical clocks, but not of atomic clocks, but nuclear clocks. The faster you can get your clock to tick, frequencies are the easiest thing to measure. You count how many times a thing happens over a chunk of time. And you get more and more precise the longer you measure it. And you get more and more precise the faster the thing is oscillating. A clock that doesn't have a second hand is not as useful as a clock that does have a second hand, right?
Yeah.
So if you have a clock with a millisecond hand, suddenly now you can like time the Olympics. Whereas before you're just like, all those people ended, but I mean, my stopwatch is crap. So the faster you can get your clock to tick, the easier it is to make a really accurate one. We are at the dawn of the nuclear clock era because earlier this year, after decades of searching and narrowing it down and getting closer and closer and closer, we found the transition in thorium-229. Thorium-229 is unique amongst all atoms and isotopes because it has a nuclear bound state that is low enough in energy that you can hit it with a laser. All other nuclear transitions are X-rays or gamma rays. We do not have technology to make an X-ray or gamma ray laser. Not like a proper like laser that you can like be like, okay, this is the frequency. And that's the thing. But thorium has a very low level nuclear state, which means that if you have a laser at 148 nanometers, which is in the deep UV, but you can do it, then you're able to drive a transition between these two nuclear states. And the nucleus of an atom is way inside, behind all those electrons. So it's way more immune to all sorts of different sources of noise. So my same advisor, Jun Yi, he actually in a paper that they put on the archive, and I think it's since been published in Nature or something, in June, they built upon the successes of people in earlier months from UCLA and I'm forgetting the other big groups, but they figured out a million times more precise exactly where this transition is. And so now we'll be able to build a clock that's 100 times more precise than we had before and smaller and cheaper and easier because you can build it with solid state. It's a whole thing. Cold atom graviometers is Al Trucker's question. Do you know what that is?
I do not.
Gravimetry is the measurement of gravity. So if you have a thing that tells you how strong gravity is, can you imagine uses for that? If it's like infinitely precise?
A lot?
A lot. Such as?
Brain dead.
Think of fossil fuels. Think about it.
Okay.
Right? Mining, sinkhole detection in Florida, mapping the topography of the ocean. If there's an underwater mountain, there's more water above it because the gravity of the mountain pulls in some water. The altitude of the ocean is only uniform if you use a definition that says that's sort of circular in that sense. Like if you measure like the sea level as being like the equal potential position of still water, then like it's by definition sea level. If you measure it from the distance from a specific point at the center of the earth, however, it's not level. Because underwater mountains have a bunch of mass and they have gravity, which means that water from the size sort of gets pulled in towards it. So you could use it for detecting that. You could use it for seismology. You could use it for all sorts of reasons. The thing, however, that's probably the most awesome is using it specifically for navigation generally. Inertial navigation. Inertial navigation is when you say, okay, I'm in a room. I'm in a windowless van because I'm being kidnapped. Okay, Maya is kidnapping me because she is unhappy with the amount of reparations that I've paid. This is a problem that comes up a lot. I get kidnapped like 3-4 times a week, because I'm not paying enough reparations to Maya. So Maya puts me in a white windowless van, and I have to be like, okay, I was able to smuggle a cell phone using my prison wallet, right? And I take out the cell phone and I call the thing, and they're like, "Where are you?" And I'm like, "Can't you just track my cell phone?" And they're like, "No, we can't, because this is Maryland. We don't have that technology." And I'm like, "Okay, well, I can tell that I accelerated in this direction for this long, and then I turned around and I accelerated in this direction for this long, and then I accelerated in this direction for this long." Even though I can't see outside the windowless van that Maya has kidnapped me in, I can still deduce exactly where I am if my accelerometer is accurate enough.
It's your cell phone has your cell phone has a built-in accelerometer.
All of them do. Most of them have like 3 or 4,
Uh,
but they're not accurate enough to do that. No. And one of the reasons is because if it's very accurate, if you're on a plane and you think that your downward, like you think that your acceleration this way is this amount, but you're off by 1%, after an hour, 1% is several miles, right?
Yeah.
But if it's accurate to a part in a billion, and oh, there's a mountain here. When I approach the mountain, I'm going to get pulled forward a little bit. And so my accelerometer is going to say I'm not accelerating as much, but I still am. And then when I pass the mountain, the accelerometer is going to say I'm accelerating more because the mountain's sort of pulling me back a little bit. So what they want to do is put extremely precise gravity measuring devices in planes and fly them around and measure the gravity locally everywhere. And if you measure the gravity locally everywhere, then as you fly, you can take that effect out, and you can be like, okay, just by paying attention to the reading of this instrument, even though I'm locked in this room because Maya is evil, I know where I am. Because you're using dead reckoning from an inertial sensor. It's sort of like, I mean, if you're kidnapped, like actually kidnapped, and they put you in a thing, and the driver is really aggressive and takes 2 really hard right turns and then 2 really hard left turns, you'll probably be able to keep up with that, right? That can be legitimately useful.
Yeah. You mentioned at least in Olympic they have a millisecond clock. How precise can our clocks be now? Like, is it milli, nano, whatever? I don't know how small
it's well below that. So if you measure for a period of time, the way you measure this is in fractional uncertainty. So if I measure for a period of time t, how much can I be off by how long t is? And if you have like milli precision, part in 1,000 precision, that means, okay, I think it's been 1,000 seconds. You could be off by up to 1 second. If you have part in a million precision, you could be off by 1 microsecond. If it's over 1 second. These clocks have a fractional uncertainty of 10 to the negative 19. That is less than a billionth of a billionth. That you would have to the clock would have to be running for significantly longer than the age of the universe to be off by 1 second. That's nuts.
Who here wants to wait for 15 billion, like 13 billion years?
Yeah, I can't do that.
Oh.
I think I've mostly covered the things that I kind of wanted to cover. So I am absolutely willing to answer questions and all that.
Yeah, I think mainly the questions are coming from Al Trucker at this point. Next one, he's asked.
Ours probably not. I wonder, do I have it? No, I guess I don't. I have a favorite paper about this, by the way. Absolute airborne graviometry with a cold atom sensor. There it is. I will go ahead and put this in the. I am wrenched. Okay. So I put the link to the archive paper in the chat, and let me share it here. Whoops. There we go. So the title of this paper: Absolute Airborne Graviometry with a Cold Atom Sensor. The reasons that you use cold atoms would require another 30 minutes. But you do it with interferometry by looking at atoms and zapping them with lasers and putting them into a superposition, then bringing them back together and looking at the patterns that emerge. And what they did was they took this device and they made it portable, and then they did a whole bunch of measurements by shaking it. This device here is to shake it. And so they could characterize it and figure out how to average out all the systematic effects from shaking it. They're trying to make a super precise accelerometer. And then they took that and they flew it over Iceland. This is a map of Iceland. This is a map of Iceland with the track of a plane that they put in ultra cold atom experiment. They put the ultra cold atoms on a plane, and they used the motion sensor, because the thing is, planes vibrate a lot, which is why they had to use the motion sensor to like calibrate the thing. And they flew this thing back and forth over Iceland. And this is the raw data before they used their calibration and stuff. And this is my favorite plot. So this right here, I want you to look at this row, C. And A and C a little, but mostly C. This is them flying over Iceland in like a grid path, and they're going east to west. But first they're going east to west here between minute 50 and minute 70. They're going from east to west, which is against the direction of Earth's rotation. Then they turn around and they go west to east. And when you're going with the Earth's rotation, gravity gets weaker because you're already accelerating down. And the fact that this line right here suddenly dips, that is a measurement of a specific phenomenon called the Edavos effect. That is the measurement showing that a scale on their plane for a 1 kilogram weight is a little bit more than 1 kilogram when they're flying west, and a little bit less than 1 kilogram when they're flying east, for example. So these things over here, these are like mountains and stuff that they're flying over, but this is just the direction.
So you're wrong. Is that why it takes 2 hours to go from Ohio to California, but 8 hours to go from California to Ohio?
Well, no, that's because time zones are black magic.
Okay.
And they went forward and they went backward, and they get like, except for this area right in between, which is like a little bit wonky. They get very like precise measurements. Like this is a map. There's a mountain right there, and there's another mountain here. And by flying over it and by looking at their instrument, they can tell where they are. I mean, here they already know where they are, and like they're not using this to do that yet. But that's the idea, is eventually this technology will become so precise that it will become more accurate or as accurate as just having a GPS connection. The thing about GPS connection, though, is that you need the satellite to work. This, if you're in a box and you make your thing work really well and you hook it up to a battery and it's going and that nobody can get into that room, it's like having a compass, but a compass that works more accurately than a compass does.
All
So
right. Okay, so last two questions we have so far are, yes, from Al again.
no, this is not related to superconductivity, unfortunately.
And finally, his last question is,
oh man, I don't know. So for those of you who don't know, Alan is a flat earther who runs the Space Audits channel on YouTube. He's a nice enough guy. I would consider him a friend, not like a super close friend, but he made me a mod on his channel like 3 seconds after I started watching his channel, literally, which is really weird. But yeah, he's a flat earther who thinks that he understands special and general relativity, but he doesn't. It's a hard topic, okay? Like, not understanding general relativity is not a knock against a person. It's not even a knock against a physicist, okay? I have never taken a class on general relativity. I'm slowly trying to learn it, but I'm doing it like in my free time.
general relativity. That's the thing that upgraded the theory of gravity or something. Or
yeah. It describes gravity as the curvature of space-time. Hello, Caden.
Now, you mentioned how to slow down atoms and stuff. Do you ever speed them up or just slow them down?
We don't speed them up generally, but you can. If instead of making the lasers all be tuned so that only atoms that are moving against them absorb the light, you can make it so only atoms moving away from them absorb the light, and you can accelerate atoms that way.
So instead of 6 of them going towards each other, they come away from each other.
Yeah. And yeah, so you can do it that way.
All right. So anything coming up that you want to advertise or plug or anything?
So my kidnapper, Maya, who unfortunately did not seem to be like watching closely enough to actually catch up on the fact that I was directly accusing her of a fairly serious crime, for which she is absolutely guilty. Maya Adkisson has kidnapped me against my will on multiple occasions, and I would like to press charges. God, I hope that nobody takes me up on it, because I am, of course, lying. I wouldn't lie. But yeah, Bad Science Sunday tomorrow. Let me just make sure that I know who the guest is, so I don't want to misspeak. Wilberforce. Our guest will be Wilberforce. So I don't know exactly what we will be discussing.
Well, as for me, the next month is pretty much open right now. I don't have many guests lined up So if I have an episode coming up soon, but I will have. But on November 23rd, I will have an episode when Jillian will return to the channel to talk about the Mayflower Compact. We're on time for Thanksgiving.
Cool.
So, if you have one, you want to say your catchphrase?
I don't really have one. The closest thing I have to a catchphrase is "Yo, what up, chat," which is generally what I say when I join a chat.
All right. You should work on one. You should work on one.
Yeah, I've thought about it. It's one of the other reasons that I don't make content is like you got to have all that stuff figured out, and I don't know what I would do. Hello, Curious People. Hello, Curious People is one that I've thought about. You know, Anton? Anton is like a science communicator on YouTube, and he does Hello, Wonderful People.
That's more of because that's more of an intro than an outro, I think.
Yeah, exactly. I don't know. I don't really have an outro other than I sincerely hope that somebody calls the cops on Maya Atkinson because she has kidnapped me.
That could be your outro. Say that on your next Bad Science Sunday at the end. But real fast. Speaking of flat Earth, I heard there's something about. I heard they're trying to not flat Earth. They're trying to host like a 2-day or 3-day.
The final experiment. It's like a week. It's a week-long trip to Antarctica. Is that what you're talking about?
Yeah.
Yeah, the final experiment. Professor Dave, actually, I just watched that earlier today. I hadn't been able to take a look at it, but while I was cleaning my place, I listened to that earlier. They're going to Antarctica with hopefully some flat earthers and globe earthers, and the idea is to observe the 24-hour sun, which should be visible in December, even on the edge of Antarctica. You don't have to be right at the South Pole. Right at the South Pole, you have 24-hour sun, I think technically half the year. Exactly half the year, I think. But even at the edge, which you can like go to for a lot less money, you can see a 24-hour sun in December. That doesn't make sense on a flat Earth.
Yeah, I saw that video. I listened to that video last night at work, and it's like they were saying, "Oh, they're going to show us a fake sun," something like that.
That's what some of them are saying. Like the one. So there's one guy that's going who I think is like as honest as flat earthers come, and that's Jaren. Jaren from Jarenism, I think, is as honest as flat earthers come. That are still flat earthers. There's people like Raichi. Raichi is an ex-flat earther. So she doesn't count. But I think that he's going to go and he's going to see the 24-hour sun, and because he has acknowledged after the challenge was put out, he has acknowledged that is incompatible with our model.
Yeah. I also heard one of the flat earthers is also a Nazi or something. I don't know.
Oh, a lot of them are. Witsit got called out hardcore last week by MC Toon for promoting white nationalism. Eric Dubé is just, I mean, quiet part out loud the whole effing time.
So not only are they stupid, they're also racist or bigots.
I mean, the two are correlated.
And with that depressing note, never stop learning and enjoy the randomness. I'll see you whenever. Bye.